University. And the title of his talk is Algebraizability of Germs and Homomorphic Foliations.
Thank you.
Thank you.
Okay, so first of all, thanks a lot to the organizers for inviting me. It is a great pleasure to be here in this occasion and talk about this. So I'm going to talk about singular homomorphic foliations. I was hoping that during the courses we would talk a little more about singularities and the local theory around singularities. But okay, so I'll just say a few things to relate these with okay, is it better now? Okay, thank you. Yeah, so I'll just say a few words to relate these, which I will be speaking about, with the previous courses, and hopefully later in the week everything will be more clear for people who are not from the area. So, okay, so what am I going to be talking about? Okay, so I said it's germs of holomorphic foliations, and definitely we want to consider germs around a singularity, otherwise it will be not very interesting. So I'm going to consider germs of singularities defined, say, on an open neighborhood around the origin in C2, so we have planar singularities, and we have foliations by curves. So the idea here is going to be that 0 is going to be an isolated singular point, and then we have a honest holomorphic foliation outside of 0, right? So we have several equivalent ways to define such a thing. I mean, what I just said is a definition, right? Outside of 0, we have a holomorphic foliation. But it turns out that we can induce this foliation in several ways. So one of them, which is something we've been doing, is considering something like this, I think. So these kind of differential equations are the ones that appear most commonly today. Just one remark, I'm not saying that these are polynomials. I am considering, like I allow P and Q to be arbitrary holomorphic functions defined in a neighborhood of 0. So this is one way in which we can get foliations like that. So, okay, let me write the other ones. Another way in which we can view the same foliation but given by differential equations in a different way is to get a system of differential equations dy dt equals p of xy. So we consider the phase portrait of this autonomous system of differential equations on the plane, and it will give us the same foliation. And because of that, we can also think about vector fields, right? So we can think of this system of differential equations as given by one vector field, which should be something like this. I think P goes with Y, so this is Y here, and then, oh, sure, let's see. And then note that outside of 0, which is the only place where these vanish at the same time, this vector, it's a tangent vector, right? And it's actually going to be tangent to the curve, the leaf of the foliation that passes through a given point. Is always, the vector field is always tangent to these leaves, right? So there are two ways in which we can define this one-dimensional subspace of the tangent space. One of them is by specifying a non-zero vector, and then the other one is by specifying a one form and considering the kernel of that one form at the given point. So we can also get this one form. So we see that that is the one form that exactly kills vector field at every point, right? So, okay, and what I said that we want 0 to be the only, like an isolated singular point, we mean that the set of points where p equals q equals 0 is just the origin. So in general, this set will define the singular set of these different objects, and I am assuming that it is an isolated point. So I just wanted to say this quickly, so that you know that if I talk about one forms of this style, it's the same as talking about vector fields like this. Actually, it kind of makes sense, right? But we can also talk about systems of differential equations or vector fields on the plane. So these are different ways of talking about the same foliation, and sometimes it's more convenient to talk about one or the other, but it's all the same, different ways of calling the same object, right? Are there any questions about this? Okay, so I will be talking today about, I will be using one forms. So I want to consider the following problem. We have the germ of a foliation around the origin on C2. And we would like to know when does this germ actually come from the singularity of a foliation on some projective algebraic surface, right? So that's why the title of the talk is Algebraizability of Germs of Homomorphic Foliations. That's what I'm gonna mean when I say algebraizable. So let me give the definition. I'm going to just write a germ, but I mean the germ of a singular holomorphic foliation. Okay, probably I'll draw a picture first and then give the definition. So we have some germ defined in some open neighborhood. And a foliation, a singular foliation, probably looks something like this. Okay? So I want to ask whether or not there exists an algebraic surface S, a foliation on this surface by curves, and a singularity, a point in this surface, such that we can realize our original germ as the germ of this algebraic foliation on some small local coordinate chart. Okay? So if there is this Okay. So I'm going to say that a given germ is algebraizable if I can find this algebraic surface an algebraic foliation on it. Actually, any holomorphic foliation is algebraic, but I just want to emphasize that we are in a completely algebraic situation here. And a point P such that our given germ is conjugate to the germ of f at P. And then by conjugate, I just mean that on a small neighborhood, we have a biholomorphism defined that maps the singular point to the singular point, and every leaf of the foliation into a leaf of the foliation here. So it transforms in a holomorphic way this germ into this germ. So, okay, that is the problem we're interested in and I would like to talk about. Sorry?
Is the example of non-conjugate?
Yes. So that's exactly what I want to say. Here is this. Okay, so a classical result in this direction is that for foliations given by a one form which have a very nice linear part, say a generic linear part, we can always choose an analytic change of coordinates in which the foliation is given by a linear one form. We say that the one form is linearizable. So so I think probably we'll see more about this later in the week. So I won't go into detail. So the idea is that if you have a nice linear part, then if you have a very nice linear part, then you are conjugate to the linear part itself. If you have a somewhat nice but not super nice one, you conjugate to a polynomial one form. So you can make changes of coordinates in which you kill the other terms in the power series so that there's only finitely many of them. But if there's only finitely many of them, you are a polynomial one form. And then obviously a polynomial one form gives you an algebraic foliation on the algebraic surface P2, the complex projective plane. So polynomial forms are a very particular case of algebraizable germs. They are those which are algebraic on the simplest projective surface, which is the projective plane. So this is a classical result known since the times of Poincaré and Dulac. There are other results which I will not talk about. And then more recently, there were, I think in 2010, there was a first result that implied the existence of non-algebraizable germs. So these are some germs of saddle nodes, and the proof guarantees their existence and actually shows that if you have a degenerate linear part, or say that your linear part is 0, the idea is that very likely you will not be algebraizable. So we kind of have a dichotomy, right? Nice linear part means you are algebraizable, and then degenerate or 0 linear part means most likely you won't be algebraizable. So there were results implying the existence and somewhat the idea that almost never, like you will almost never be algebraizable, but there were no concrete examples about it. Okay, so what I wanted to present today is a concrete example that we constructed with Frank during the summer, and it is the first concrete example of a non-algebraizable germ. So I'm going to erase this and write the expression here. Okay, let me write it like this. I'm going to give you a one form, which is going to induce this foliation. Okay, so what is this? This omega 0, I'm not going to write it down, but it's pretty much, this is something you can choose. You can make any generic choice, and this is going to be a quadratic homogeneous one form. So note that this is the terms of degree 2. And then since I'm starting here with x squared and I have already degree 1 here, these terms are terms of degree 3 and higher. So in particular, this is a one form which has 0 linear part. And then the first non-zero jet is the quadratic part. And what I'm saying is you can choose pretty much whichever quadratic part you like, and then the result will work. I just don't want to give an explicit expression because it's not relevant. But it's just choose almost any quadratic homogeneous part. And then the higher order terms are these. We have a power series that only depends on x, and it has these weird coefficients, exponentials of square roots of integers, minus so that it actually gives a convergent power series. And this other term right here, which I'm going to call R. So let me draw here. Okay, so a generic quadratic homogeneous one form will define a foliation with 3 invariant lines. And a singularity, and then the other leaves do not accumulate into the origin. And then the other term there that I wrote R is actually defines the radial foliation. It's the foliation by lines through the origin. And then this combination, the fact that we have this quadratic part plus a multiple of the radial foliation, means that my one form, omega, still has these 3 invariant lines. And then the drawing is going to be very similar to that one, although the foliations are very different. This is a very simple foliation because it's just given by a quadratic homogeneous one form, and this is pretty complicated. What I just wanted to emphasize is the invariant lines. So we have these invariant lines, and this is like a very rich foliation. It encodes a lot of information, and on the other hand, this is pretty simple. So okay, so that is my construction, and then I want to say that is not algebraizable. So the main observation is the following. I chose these coefficients here like that for a reason, right? And then the idea is that if you take the rational numbers and then consider a field extension by adjoining to Q each of these complex numbers. So we get e to the minus 1, e to the minus square root 2, e to the minus square root 3, and so on. This is going to be a field extension of infinite transcendence degree, meaning that not only is not algebraic over Q, I'm adding these transcendental numbers, but moreover, the transcendence degree is infinite. I'm adding infinitely many algebraically independent complex numbers. So it is a big field extension. So it's as big as it can be, like given that I'm adding countably many numbers to Q.
Is it completely obvious that they are algebraically independent?
It follows from general field theory. So the exponents are linear, well, have a subset of linearly independent algebraic numbers, and then it is called Weierstrass-Lindemann theorem, that in such situation, the exponentials are going to be algebraically independent. And I'm going to be writing these TRDG as a short for transcendence degree. Okay, so the naive idea would be, okay, I'm constructing this one form and throwing in a lot of transcendental numbers in such a way that the coefficients of this one form generate a very large field extension of Q. And on the other hand, if I have a polynomial one form, the fact that it's polynomial, it means that it's defined by finitely many coefficients, right? It has finitely many terms in the power series expansion. So if you take a polynomial one form and then take a field extension of Q by adjoining those coefficients, we get something of finite transcendence degree because we only added finitely many complex numbers, right? So that's the naive idea. It makes somewhat sense to hope for that, but then there's an obvious gap. If I take a polynomial one form and make any, like an arbitrary change of coordinates, there's absolutely no reason why after the change of coordinates we get something that is still polynomial. Like most likely we won't get that. And even if it's, like it might be not polynomial and already have like a lot of coefficients which would generate a large field extension. So we have to deal somehow on that freedom we have to make changes of coordinates, right? Because remember that in my drawing there was this coordinate chart from the algebraic surface to my given foliation. So that chart is arbitrary. I can choose any other coordinates. So that kind of leads to the following definition. So, okay, first of all, I'm going to write, well, let me see. I have a one form. I mean, since this is the coefficients are homomorphic functions, they always have a power series expansion. So I'm going to write Q adjoint eta to mean, I'm going to define this to be the field extension of Q obtained by adjoining the coefficients of eta. I mean the coefficients in the power series expansion of. Okay? And then I'm going to define now the transcendence degree of the one form eta to be the following. I'm going to take the minimum over all transcendence degrees. Okay, let me write it first and then okay, that's it. I'm going to consider all one forms which are analytically equivalent to my given one form. And then to consider all the fields, I would get transcendence degrees. Is it clear? So by construction, by this reason, this object which I just defined definitely is an invariant of the analytic class of the one form. If I take any other one which is analytically equivalent to it, then they clearly have the same transcendence degree. So if I take a polynomial one form, since I'm taking a minimum, any polynomial one form has finite transcendence degree, right? So if we want to construct a one form which cannot be conjugate a polynomial one form, then it is enough to construct a one form which has infinite transcendence degree. So I claim that I just did that. Okay, so that's definitely something that I need to prove. It's by no means obvious, but is it clear what I'm trying to do here? So now, because the way I define this transcendence degree, it is clear that any polynomial one form has finite transcendence degree. So as soon as I construct a one form of infinite transcendence degree, it will not be conjugate to any polynomial one form. Okay, how are we doing time? Okay. Yeah, I think I might be going a bit fast. Okay, so I want to prove that. And then the proof of that is going to be somewhat obvious from the lemma I'm going to write. Okay, so maybe at this point I should say something to help people who are not very familiar with these topics to understand better. So I have an equivalence relation here, right? Which is analytic equivalence relation. I'm going to say that these two one forms, but really I'm thinking about the foliation they define. The foliations are analytically equivalent if I can find an invertible holomorphic map that will take one foliation to the other, right? So this is saying that they are the same foliation in different coordinates, right? Like they are the same on their change of coordinates. So once we have an object and an equivalence relation, we would like to classify those objects up to our equivalence relation. So we want to find invariants and try to prove that if the set of invariants equals, like if you have two foliations with equal set of invariants, then they're going to be analytically equivalent, and your invariance should be up to like invariance of the analytic class. So you kind of want to say that the foliations will be equivalent if and only if their set of invariants are the same. So that's a very natural thing to do. And another very natural thing to do is to introduce normal forms. So a normal form is amongst all the equivalents, like all the elements in the equivalent class of a foliation, we single out one which for some reason we can say that it's the nicest. And then this good representative should have something like the property of two objects are going to be equivalent if and only if they have the same normal form, right? So it should be up to some extent unique so that it allows us to decide if two objects were equivalent or not by moving to their like canonical, well, like their nice representative normal form and looking at the normal form, right? So in order to prove this, I'm going to rely on a classification theorem of this class of foliations. So what I have here is a one form with vanishing linear part and then generic quadratic part. So a complete analytic classification of such foliations was obtained by Laura Ortiz, Ernesto Rosales, and Sergei Voronin. And they give a complete classification of analytic and normal, a complete set of invariants and normal forms for analytic and formal classification of these germs of degenerate singularities, starting with a generic quadratic term. So my lemma is going to be the following. Okay, so let me see. Let eta be a one form and I'm going to call eta hat the formal normal form of eta. Actually, this normal form is analytic, so I'm going to say it's analytic normal. Let me read. Okay, so I'm going to claim that the transcendence degree of eta, namely the minimum transcendence degree over all these possible extensions, this minimum is achieved at the formal normal form. So let me say the transcendence degree of eta, which is the minimum of all these transcendence degrees, okay, so this normal form not only is used to give a complete classification of these types of foliations, it also turns out that if I care about this transcendence degree, then the only thing I need to do is look at the normal form and check the transcendence degree of the field extension obtained by taking Q and adjoining all the coefficients in the normal form. And that's going to be the optimal way to minimize that transcendence degree. And then I still need to say some words about the proof of that, but just fact here. This form was given like this because it's already in its normal form. So it was, deliberately constructed in this, like having this form, so that it is already in its normal form. And then it is clear that if I take, I just said, right? If I take all these coefficients and adjoin them to Q, I get a field extension of infinite transcendence degree. And because of this lemma, this is as good as I can get. So this lemma implies right away that this one form has infinite transcendence degree, and hence is not conjugate to a polynomial one form on the plane. So now the only thing I need to do is prove this lemma, and I think I've been saying this a lot, but now this lemma is obvious from the proof that these authors provide. In the paper where this normal form is introduced, they take a one form and then they make successive changes of polynomial changes of coordinates to modify the power series and take the one form given into its normal form here. But actually, a careful reading of this construction shows that at every step, they are defining a change of coordinates by solving a bunch of linear equations. So these linear equations are defined over the field of coefficients of eta. And then if you solve a linear equation here, the solution is also going to be on the same field. So they never leave the field where the coefficients of eta live. So in particular, they arrive to a normal form, and all the coefficients in the normal form live in the same field as the coefficients of eta. But now, it might not be true that if we take the coefficients of the normal form and adjoin it to Q, we're going to recover the same field. Probably the field is going to become smaller in the process. But at least, so let me write it here.
And that is unique?
Well, they give a construction how to obtain it. As they define the normal form, is not exactly unique. It has 1 degree of freedom, which is multiplying everything, well, making a homotopy, and then multiplying by another scalar not to modify this element, but there is 1 degree of freedom. So there's something that I should be more precise about, but I'm just going to ignore that and kind of assume that it's unique, but it's almost unique.
So at some point you have to prove that this homotopy doesn't change the extent.
Well, it could actually, but it will not change the fact, like if the transcendence degree is finite or infinite, that one parameter cannot change that. So actually what I'm saying is not exactly true, but for the purpose I care about, it is. Okay, so what I was about to write was that the construction of the normal form proves that this field is contained here. So it might be a proper subfield, it might be considerably smaller, but I mean, this is enough to prove that the transcendence degree of those fields is at least as small as the other one. So I mean, if the transcendence degree was not minimized at the normal form, it would be minimized at some other one form. And then I do this to obtain the normal form and see that the transcendence degree at the normal form is actually as small as the other one. So we definitely achieved the minimum here. So that proves my claim. So does anyone not believe that I proved that? I mean, if you believe my claims, but the idea is a very simple one, right? Polynomial one forms are defined by finitely many complex numbers. So if I take those complex numbers and adjoin them to Q, I'm going to get a small field extension, a field extension of finite transcendence degree. And then the way I constructed this one form was such that the coefficients are going to generate a large field extension. And because this one form is already in its normal form, then I cannot decrease the transcendence degree. So any other one form is going to have at least as much transcendence in its coefficients as this object. Because I buried the transcendence not just in the coefficients defining the foliation, I made sure that they were in something invariant, in the normal form that completely classifies and allows us to decide if two one forms are equivalent or not. So this is well built into the invariance of the foliation, not just on the coefficients, because the coefficients can be changed by a change of coordinate. But then the analytic invariance cannot. So this is embedded in the analytic invariance. So So at this moment, I only proved that the one form is not conjugate to a polynomial one form. So it means that the foliation, the germ of the foliation it defines is not conjugate to the singularity of an algebraic foliation on the projective plane. So an interesting question would be like, oh, well, it's not conjugate to a singularity of a foliation on the projective plane, but what about other algebraic surfaces? So I'm not going to go into details, but the way I did this is enough, because if I have a projective algebraic surface and an algebraic foliation on it, both objects are defined by finitely many complex numbers, right? So an algebraic variety on projective space is defined by finitely many rational functions, and each rational function is defined by finitely many coefficients. So every time I have an algebraic foliation in some algebraic variety, it is completely defined by finitely many complex numbers. So this same argument works just the same.
Can't you say that the smooth point on an algebraic surface is obtained from the plane by an atomic?
I guess in the end that's the argument. You can always take this singularity and kind of like push it now to the plane, and then you have the same.
What you're doing, I think, is invariant for atomic stations.
Okay, let me think, because if you have a foliation on the projected plane, you can pull it back to your cover. But if you have a foliation on the cover, can you push it down to the plane? Not globally, I think. But locally, yes, and all the analysis is local. But the idea is essentially the same. Okay, so that's all I'm going to say about this construction. And now I just want to like mention a few interesting problems. So first of all, it would be very interesting to see what does it mean geometrically that a foliation is algebraizable or not. So if I'm given just kind of like the portrait of the foliation and not the equation, can I decide if it's algebraizable or not? And then another question would be, okay, if it's not algebraic, I mean, can you kind of decide on which algebraic surfaces you can realize your singularities and in which ones you cannot? And then some other question that came like earlier is, suppose you are actually not only algebraizable, but you are conjugate to a polynomial one form on the projective plane. Can you say something about the degree of that polynomial one form? Can you give a bound as what is the optimal degree which you can achieve? So also this definition of the transcendence degree of one form is just kind of like a technical definition to be able to state the theorem better, and it looks very transparent. I think it's like I think it's a good way to communicate to the listener like why that one form defines a foliation which is not algebraizable. But then it would be interesting to see if there's any implication, once again, in the geometry of the foliation. I mean, does a foliation with infinite transcendence degree look different with one of finite transcendence degree? Does a foliation with 0 transcendence degree look different from other ones? So, yeah, so those are some questions I haven't thought about, but would be interesting to do so. So thank you, that's it.
Any question or comment?
Yeah?
This is just sheer curiosity. But you said that the quadratic form, the omega 0,
Yeah.
had 3 invariant lines,
Yes.
and then something kind of subtle.
Yes.
And then you said that the one that is not algebraizable, you painted pretty much the same picture.
Yeah.
So is it because it's in C2 and the weird things happen in somewhere else, or what's the?
So the reason of that is that this has three invariant lines. And then this radial foliation has every line through the origin invariant. So if I add them up, I'm going to get something that has at least these three lines invariant, right? Because, I mean, so what does it mean to be invariant? It means that the one form is giving you a linear subspace of the tangent space, right? But if it's invariant, it means that at every point in the line, you're getting the same line, right? So you're getting the line here and then the same line here. So globally, like the sum of them is still going to be invariant. So it's just like because of the way it's constructed. It's not something interesting. The interesting part is that if I take a I mean that it's not necessarily true that the higher order terms are a multiple of the radial foliation, then no longer I will have three invariant lines, but I will have three analytic curves intersecting transversally, right? So it's gonna look different. Like I'm gonna still have the same behavior, but then I can do this, right? And then the thing is, I have three analytic curves here, and actually I can find a change of coordinates that will rectify the three of them at the same time, right? So I can do that, and then anytime I have a foliation like this, it is going to be conjugate to another foliation which has three invariant lines. So that's good for three lines. If I have more, then it will not be true that I can always do that. But the fact that quadratic is kind of like low degree allows me to always rectify simultaneously the three separatists.
Thank you.
Any other question? Well, let's thank Valente. Usually we have a last talk today.